Hey, through the magic of editing, the spectrogram you see on this slide is the spectrogram of the sound that I just made. Let's look at that sound in a little bit more detail. This is the short-term Fourier transform of the chirp I made in the whistle. Like we saw in the last episode, my hands has a resonance of around 500 hertz, which is about here. Here's I'm whistling, I open my hand and there's a little bit of a chirp in the sound, which you see the frequency increasing, and then as I close the hand it comes back to 500 kilohertz. Okay, so this is the spectrogram of the data showing the Fourier transform as a function of time. Let's look on the next slide at the actual data. So this data was sampled at 22,000 times per second, which means that if we go over 1 millisecond from here to here, we count out about 22 samples. Now, what's interesting is that in the episode 2, we talked about how we can represent continuous signals discretely using their Fourier components, but that's not what happens here. This signal is represented by discrete samples of the signal at a specific time. This video discusses why this is allowed. After this video, we'll also understand why we get this approximate spectral range for the frequencies. If we sample at 22,000 times per second, the maximum frequency we should observe will be about 11,000 hertz. We'll talk about how that works in the rest of this video. Computational imaging. Episode 4, Sampling and Discrete Analysis. We're talking about computational optical imaging. We're in Chapter 2, looking at forward models. We're in Section 2.4, talking about sampling and discrete analysis. Back in Episode 2, we talked about functions with limited support on V sub L, the vector space of functions such that the function is defined for magnitude of x less than L over 2, but is equal to 0 for x greater than L over 2 or less than minus L over 2. We were able to show that such functions are described by a Fourier series, with the Fourier coefficients being given by the projection of the function onto each Fourier component over the support. We also talked about band-limited functions. This is a function for a Fourier series where the coefficient goes to 0 for some frequency, but we can also think of a continuous band-limited function. So here we're looking at the function f of x. It has a Fourier transform f hat of u, and we're just going to say the function is band-limited if the Fourier transform is 0 for magnitude of u greater than b. Such a function has limited support, so it can be described by a Fourier series in the Fourier space. Now, we want to force the function to be band-limited, so we can multiply it by a rect, otherwise it would be periodic. So this rect has the property that goes to 0 at the argument equal to 0.5 or minus 0.5, and then it's 1 in between. And so in this case, if u is less than b, the rect would be equal to 1, but if u is greater than b or less than minus b, the rect would be equal to 0. So we have a periodic function from the Fourier series which is limited to the band by the rect function. So for any band-limited function, this is a complete description of its Fourier transform. We can take the Fourier transform, the inverse Fourier transform of our Fourier transform, and recover the original function. So this is the original function. It's using the same expansion coefficients in a series, but now we've replaced the harmonic function with the sinc. The sinc is the Fourier transform of the rect function, sine of pi x over pi x. And the sincs are shifted in the series because they're convolved with the Fourier transform of the exponentials, which of course is the Dirac delta functions. So we have a series of sincs at different centers. The sinc looks like this. It has a property when x is equal to 0, it goes to 1. For all other integer values of x, for example here at x equals 1 or x equals 2, the sinc was equal to 0. So for any band-limited function, this expansion is an exact description of the function as a function of x. Now we can evaluate these expansion coefficient f hat of n by using the Fourier series analysis as we did in episode 2, or we can look at the fact that we can use the zeros of the sinc. So if we look at this function, and we evaluated it for some particular value. Here, let's say that we're going to evaluate it at f of n prime over 2b. So that x is equal to n prime over 2b. Now the 2b will cancel, so what we'll get here is just sinc of n prime minus n, which is equal to 0 unless n prime is equal to n. So what we would recover here would be f hat of n. So we see that the function f of x evaluated at any integer n over 2b is equal to the expansion coefficient corresponding to that point. So we can expand f of x in terms of these samples. These are sample values of the function evaluated at x is equal to n over 2b, and then expanded in a series with the sinc as an interpolating function. So for any band-limited function, this is an exact representation of the function with discrete values at the sample points rather than continuous values over space. This is called the Whittaker-Shannon sampling theorem. It tells us that if we sample the function at these discrete points, we can represent the function exactly. Now, there's a requirement on the sampling rate that the sampling period has to be less than 1 over 2b, where b would be the actual bandwidth of the function. This came up in our definition of the bandwidth that also determined the sampling rate that we have to get. Basically, we set our samples at delta x is equal to 1 over 2b. If we undersample, we will get aliasing effects, as we'll see later on in today's discussion. Okay, so now we can take the continuous function and represent it by its samples. If we just measure those sample points, we have an exact representation of the function, and then we could go back into the Fourier series analysis, or the Fourier series representation of the Fourier transform of the function, and write that as a sum over these discrete values in functional space. So now we have a continuous representation of the Fourier transform of the function using these discrete values where the expansion coefficients are f sub n over 2b. Now, a lot of times we would like to have discrete forms both in the Fourier space and in the and in real space because we'll implement the Fourier transform using discrete analysis as well. So when we think about this, we'll look at this expansion of the function and say, well, so first of all, the expansion in the Fourier series, it goes over infinity, so we have to take infinitely many samples at these discrete sampling rates to accurately represent the Fourier transform of the function. But a lot of times the function, is only considered over a finite window in space, so we'll truncate that series and say there's some maximum value of x equals to, in this case, x would be equal to n over 4b would be the maximum value of x that we would want to consider, and assuming that's large enough to fully consider our function, we can turn this Fourier series representation of the Fourier transform into a finite sum, and then we'll evaluate that sum at specific values. And specifically, we assume that the spacing that we need in the Fourier series or the Fourier space is delta u would be 1 over 2x, where x, big X here, would be the spatial extent of the function in real space. And we're making this assumption basically in analogy with our sampling rate in the Fourier in the real space, where we had to sample at 1 over 2b. So the total number of samples that we have in the function would be 4 times bx, which for our original function, since x is the spatial extent of the function, or 2x is the spatial extent of the function, and 1 over 2b is our sampling rate. So our sampling rate would be, so we'd have delta x, or big X, or 2 big X over delta x, which would be 4xb, would be the total number of samples that we have in real space. And then we do this discrete Fourier transform of that into Fourier space, and we have the same number of samples in Fourier space. So we end up with these pairs of transforms in discrete form between the Fourier transform of the function in discrete form using what we call the discrete Fourier transform, which takes this form, and then we can inverse transform that to recover the original samples. So this is an exact relationship from the original samples to this discrete Fourier transform, and we use the discrete Fourier transform as an approximation of the actual transform of the function. So very important as we go through the analysis of looking at imaging systems. We'll very commonly consider that we have images over some extent x, which would be the half space along real space, and then the sampling rate or the extent in x is 1 over 2 times the sampling rate in Fourier space. Little x, the sampling rate in real space is 1 over twice, or 1 over the bandwidth of the signal. The bandwidth is then correspondingly 1 over 2 times little x, and similarly for the sampling in Fourier space, and the total number of samples is the space bandwidth product, or Shannon number, 4 times bx. So these numbers will come up commonly as we begin to understand what is the relationship between real samples and their Fourier coefficients. For example, when we were looking at the sound wave, we sample at a certain rate in space, or in time, as we'll talk about in just a minute, and that corresponds to a certain bandwidth in the reconstruction space. Okay, let's look at an example. Here's a function. It's a cosine, which is has a Fourier transform, which would be a delta function at, in this case, frequency 1. And it's multiplied by a Gaussian. So the Fourier transform of the Gaussian would be also a Gaussian, but since this is a Gaussian with square root of, or 1 over square root of 0.01, so it's a relatively broad Gaussian because the argument for x squared is relatively small, but its inverse will have a width of about 2, because it'll be 1 over square root of 0.01. And so if we look at this function and its Fourier transform, it looks like this. So the function is a cosinusoid, or a sinusoid modulated by this Gaussian, and then we take its Fourier transform and we see Gaussian peaks at the two positions of the plus and minus frequencies in the cosine, and the widths are relatively narrow because the function is relatively broad in real space. So here we've sampled this function relatively densely. So this is also done with discrete analysis, but this is with 1,000 samples over 20. Now, for this particular function, the bandwidth, so b, the bandwidth would be about 1. So if we would need at least the Nyquist sampling rate would be 0.5. The delta x would be 0.5. Here we're sampling at 0.4, so you can see these are now discrete samples of the function. That we see the jagged curve. We've sampled about 20% over Nyquist. So this is what the sampled signal looks like, which doesn't look like the original signal, but the Whittaker-Shannon sampling theorem told us that if we sample at this rate, we can recover the original function. And we do that by applying the Whittaker-Shannon sampling theorem. So what we would, looking at these two functions, we can look at, these are the samples. This is the Fourier transform of this function, the discrete Fourier transform of this function looks like this. This was the original function with a higher sampling rate. We see when we lower the sampling rate, what that means is that the bandwidth, when we take the Fourier transform, is 1 over 2 times the sampling rate. So if we lower the sampling rate, then the band that we cover is less. So down here, the bandwidth goes out to 10. Here, the bandwidth only goes from -1 to +1, and this 1 is approximately the extent of b, our bandwidth. But despite the fact that we have sampled at a much lower rate here, we should be able to recover the function using the interpolation theorem. And so we do that by taking the samples that we have, multiplying them by this sinc, and then adding the sincs together in this sum. And so that's what's done here. We have the original samples. Now here, these colored curves here, these are the sinks. So this is the sink at 0, this is the sink at 1, 2, and so on. And we've multiplied each sink by its Fourier coefficient, and then just plotted or by its sample, and then just plotted all the sinks together on a line. So we take all the curves that are on this line and add them together, and we recover the original signal, which is what the Whittaker-Shannon sampling theorem would predict. So that's what we've learned here, is that we can take discrete samples of a function and use them to represent the function exactly if we apply this, if we've sampled at Nyquist or better, and we apply this interpolation function. If we undersample, we get something like this. So here, instead of sampling at 0.4, which would be the Nyquist, we've sampled at 1.2, And what happens is that we've undersampled. And what this does is it aliases, it takes high frequencies and turns them into low frequencies and creates a distortion in the signal. We'll talk more about aliasing later on in the text. We return to this topic in some detail in section 7.2 of the text, where we talk about in detail about what it means to make discrete samples, where we include the impact of optics in a system and the impact of pixel sampling functions. And we'll look in detail at aliasing in imaging systems that use discrete integration on pixel planes that have actual sampling functions. But we'll wait a while to get back to that and have to talk a lot about optical systems and fields before we get there. In the meantime, let's return to the sound wave that we began this discussion with. So as I mentioned earlier in today's discussion, this wave was sampled 22,000 times per second, which means that this delta x, in this case delta t, would be 1 over 22,000 in 1 second divided by 22,000. And so our bandwidth is going to be 1 over 2 delta x, which is going to be 22,000 over 2, or about 11,000, which is kind of the extent that we get in our plot here of the bandwidth in the curve. Okay, so we've learned a lot about sampling and Fourier analysis. Next time we're going to talk about yet another way to expand functions. We started with the Fourier series. Now we've seen the Shannon interpolation function using the sinc functions. Next time we're going to talk about using wavelets to represent the function.